Okay, picking up here with second problem on the practice test. Okay, so second problem here. We've got saffrol, which, I guess from sassafras oil, used in root beer. But once we get into the data here of the problem, we've got a 2.39 gram sample. Okay, so we know the mass. Dissolved in 103 grams of diphenyl ether, mass of the solvent, so that'll be useful along the way. And this solution melts at 25.70 degrees C. We're comparing that to the normal melting point or freezing point of the pure solution, which would be 26.84 degrees C. So there's a temperature change of the freezing point that we can use. We've also got the constant down there. We want to calculate the molecular mass, right? Molecular mass, molar mass are synonyms, same thing. So molar mass is how many grams are in each mole. So we know how many grams of our sample we have. That's given in the information. We used that when we built or made the solution that we were testing. So what we really want to do here is identify how many moles of the sample there are. And that's something that we can do through colligative properties, because we can compare that change in whatever property we're describing to that measure of concentration. If we can work that measure of concentration back to moles, then we've got that information. So in this case, since we're dealing with a freezing point, we're going to want to think about this formula. The change in temperature of the freezing point is equal to the freezing point depression constant times the molality of the solution. So italicized m, lowercase m is for molality. So I made that a little artsy there in the m, right? But that's molality information. Now we've got enough information here to figure out the temperature change, and we've got the constant, so we can solve for molality here. Now, one point I want to make clear, and this will vary depending on the textbook you look at. I've seen it change from one version of the textbook to the next. For freezing point depression, sometimes the constant is considered to be a negative number, right? The temperature is going down, it's being depressed when you make a solution. If this is negative, that means you want your temperature change to be negative as well. That way the negatives cancel out. Concentration has to be positive. If you go through one of these calculations and you come up with a negative molality, you should realize that's physically impossible. You can't have less than 0 of moles of a solute in a solution. So if that's the case, you probably just didn't cancel your negatives correctly. Okay, so in this case, the constant's negative, so we'll calculate the temperature change as a negative number as well. So we will take the final temperature minus the original temperature, which would be the freezing point of the pure material, and that is negative 1.14 degrees Celsius. Okay, plug that in here. Minus 1.14 degrees C is equal to the constant, negative 8 degrees C per molal, and we're multiplying that by the concentration. So if I just divide both sides by negative 8 here, I isolate molality on one side of the equation, and then all I have to do is do that math. 1.14 divided by 8, since both the negatives cancel out, and this is 0.1425 molals. Now, we said back up here, right, we wanted to get to moles, and this is kind of the tricky part of the question, or the part of the question that will sometimes throw people off. This isn't how many moles, right? What you have to realize here is that molality is moles of solute per kilogram of solvent. It is ratioed to how much solvent is there in the solution that we're talking about. So to go from this to moles of the saffrol, we need to multiply by how much solvent was in that solution. right? And that was given up here in the problem. 103 grams of diphenyl ether would be 0.103 kilograms of the solvent. 1,000 grams in a kilogram, so divided through by 1,000, or move the decimal by 3 places. That would cancel out kilograms, and this would give us moles of our solute, which is the safrole in this case. So divide that previous, delete, multiply that previous answer by 0.103, and we get 0.01468 moles of safrole. Like I mentioned earlier, molar mass is grams per mole, so we'll take the mass provided at the beginning of the problem, divide by how many moles we just determined were in the sample from the observed change in the colligative property. So 2.39 divided by 0.01468, and that will give us our molar mass. So 3 significant figures from the mass we recorded there. So round that to 163 grams per mole. That would be our molar mass for that particular problem. Okay. Do something similar with any of the colligative properties. Right? You could do this with osmotic pressure, work your way to the molarity of the solution, and then if you know the value, you could get to moles. This would be a little trickier with vapor pressure reduction, but you could use this to figure out the mole fraction in the solution, right? Moles of solute divided by moles of solute plus moles of solvent, to work your way back to how many moles of solute are present. Okay, we'll stop that there and we'll go to a new video for the third problem.